this hot day. Okay, not working. Okay. So what is PyData? We are a community for developers and users of open source data tools and Python enthusiasts. And we are part of NAM Focus, which is is promoting open practices and is a non-profit organization. We are present in different countries and cities and have lots of groups and members. PyData Milan has a special code of conduct. So basically, be kind, be professional. We are all here to learn something new, to make connections, and be kind to each other. PyData is founded 2.5 years ago. We have 1,500 members, and in these 2.5 years, we had 25 events. We try to organize events every month, every third Wednesday of the month, usually. During the summer, we will take a break, and then we will see each other again in September. Okay, so today we want to thank also to Jacopo and Flixbus for hosting us, and also to all of our other sponsors that has been hosting us for over 2 years. And special thanks to Julia, who is always recording, to Python Software Foundation, Division Lab, and Python Italia. And today we will hear Jacopo and Francesco, who is coming. And I think that I skipped one slide, but basically I just wanted to ask you if someone is new here, if it's your first event, or you already have been. Okay, welcome. We usually have aperitif or dinner or drinks after the event, so raise a hand if you want to come with us. So we can reserve, okay. 5. Okay, 10 more or less. Great. Maybe I should find, okay, it was this one. If you want, you can scan this code, and there you can find our meetup page where you can follow us and see what the next events will be and when, and also the Python Milan group, which is also organizing events once a month, usually the first Wednesday of the month. And we have also the call for speakers, always open. So you can check it out. And if you want to present something work-related or not work-related, you don't need to be a professional. You can submit your talk. That's it. Jacopo, you can start.
Okay, it works. Somebody's coming, probably the second speaker. Okay, so this QR code is to see the slides on your phone if you want, so that you can follow the links in case there's something that you want to explore, and then you can have it later if you want to go deeper on some topics. So before starting, I'm going to present a bit Flixbus. I think you already know it, so it's not new. You know what it is. Yes? Yes. It's a bit small. Can I put it full screen, F11? What is F11? No.
Is it a presentation?
It's a web page. Okay. So yes, this is the QR code. Um, is it fine? Okay. So I think you already know Flixbus, at least by name. But something you may not know is how large Flixbus is. Flixbus operates since a few years also in India and in Australia, in the United States, South America. In particular, in the United States, Flixbus did buy Greyhound, which was well, it still exists, but it's the largest bus company in the US. And also Flixbus operates trains. Currently, all train lines are in Germany, but it's going to expand a lot in next years. And in fact, it's going to become two separate entities, Flixbus and Flixtrain. And all of this, as you can imagine, has a huge IT behind. So we operate the website, the app, but also we have stuff like network planning, this, calculating how many buses we have to put on different routes. As for me, I work on the demand forecasting. So we do statistical models, essentially very simple machine learning on demand, calculate how many people would like to buy a ticket for every route, for every stop in the future, so that we can assign a price dynamically. So in case you are interested, of course, you can ask me about the company, the work later. But here there is a link to see open positions. I think we have something now in marketing in Italy, but also abroad. Flixbus is a German company, so the main office is in Berlin and also in Munich. This office is relatively small, but still we have something. We have 4 developers here, me and other 3. Okay, so today we're going to talk about processing geographical data in Python. This is not something I work on for work, it's something I do essentially for fun. So all of this is extremely silly. There is no practical application at all, at least for me, but you may find something. So to start, I decided to put a set of examples of stuff I did, mostly in Python. I try to pick up the ones that are more Python related to give you an idea of what you can do by processing geographical data. And this is an example of an heat map of the BikeMI station usage over a day. In fact, this is a website you can visit if it works. If it works. So this, okay. I have to press, okay. So this shows you how over time, on an average day, stations of the BikeMI service are used in Milan. So this is done by scraping, by calling the BikeMI APIs a lot. And this is just an example of how you can display something interesting on a page. This is something a bit quite more complicated and is a reachability map of the stations, the metro stations in Milan. So this shows every area that you can see here is all the places from which reaching a specific station of the metro is the quickest option. And this considers not distance, that will be just a Voronoi map, that's not interesting. This considers the road network, so how much time it takes to move around by walking, or the tram and bus network. So it actually calculates the schedule of the bus, how often it passes, and how easily you can reach a stop and not another. This is interactive, but I'm not good and see. You can just see this data also on your phone. And the same data can be displayed as a heat map. So you can see the different colors here represent the distance of each area in Milan from the nearest metro station. This is something a bit quite more silly, but it's still working. This is a Telegram channel I have that basically detects when I'm in a new street in Milan for the first time since I implemented it, or a city still in Italy. And when it happens, it just sends me a message. So it's just a gamification of moving. And that's it. This channel is public, but I don't think you are interested in seeing where I go. This is another representation of the same data. This is a heat map representing the places in a city. In this case, it's Berlin, where I am more often. This is another example. This is a static address index. So basically, this is a map that is completely self-hosted, is on Nginx. So there is no backend, no cloud service, nothing, just a server offering files. This is relatively easy to do. But the nice thing is that this offers also indexing of addresses. So you can see here, I search Pizzeria da Pino, which is a pizzeria near here. And this thing can do the search and find it without a backend, only serving static files. And this works for the whole Italy. So it's 13 gigabytes of data on an Nginx file, and it works. And here you can find the code. So there is code and article explaining everything. This is the only example in here that is actually useful, that I actually use for a real purpose. Essentially, I'm in an association that needs often to do a car trip of Milan and visit a few points. So we have a list of addresses, and we need to visit all of them, or most of them. And so I created a tool to solve this issue by first locating the addresses that are in natural language on the map. Somebody has to open to the guy. And then by calculating the distance and the travel path between one and the other, which means we have to keep track of the speed limit and the presence of traffic lights. So this is taken into account. And then we have to find out the best order to visit them. This, probably you know, it's the traveling salesman problem. It's very hard. I don't solve it. I just find I use an heuristic that finds a decent solution, and it works fine. So what all of this stuff has in common is that in any case, we need to create a software that is able, in our case in Python, but also the languages, to be aware of space. So it needs to know where something is and needs to be able to understand when something intersects something else, when a point is in a position or another. So it needs to be able to process space. And this is what you're going to see. So the first thing you need is, of course, data. So you need to know where a street is, what are the speed limits, where a city is, stuff like that. And the first source that you can see is GTFS. GTFS is the standard format for public transport data. So if you want to know what is the schedule of the buses on a city or where the metros are, you can download it. Pretty much for every city, every provider, there is something. ATM in Milan has one, so you can download it. That's what I used. And Flixbus also has one as well. So if you click on that link, you can download this data. And there are many tools to analyze this data. In particular, what I suggest is R5Py. This is a wrapper around a Java thing. Sadly, there are like 5 Python tools that can do this, but they all do terribly. This thing actually works in reality. So you don't spend one day setting up mysterious config files. This actually works immediately. And this is an example. This is how you can calculate the travel time between a few origin destinations in the city of Helsinki. And this part is the interesting one. You need 3 sources of data. One is the road network, which we're going to see in a few slides, how it's defined, but basically it's a file that you provide. The second is, of course, GTFS. It's optional. You can also just go with walking and ignore public transport. And optionally, I didn't use it for Milan, you can provide elevation data. So basically tell it how does the land look, so you can know how quick you are when walking uphill or downhill, or if you can even walk uphill, because maybe the elevation is such that you need some way to go up, for example, a gondola in so some transportation, some ferry or something like that. And this is quite easy to use. So R5Py is quite powerful for this kind of analysis. The result is usually something like this. So you can create an isochrone, which is a representation of the points usually in a city. You can do it also in larger areas, the points that you can reach in time. This is much more complicated in distances because it needs to calculate how you move around. So all the streets, speed limits, traffic lights, crossing, schedules of public transport. You can see that here I have to provide the time, because when you depart, affects which public transport lines you can use. Another source of data that I didn't use here, but is very interesting, is inside Airbnb. They scrape Airbnb continuously, and they provide data about listings, so you can see the cost and how much people are using Airbnb actually. Turns out not a lot. Many apartments are just empty, but you can see it with actual data. You can see the reviews also. Then for bike sharing, most bike sharing services do provide this data. In fact, BikeMI has an API, which I used. but there is a service called citybike.s, citybikes, which provides data for pretty much all the cities in the world in Parkify. So it's amazing. You can just download all the data for historical data for bike sharing, so you can see how much people are using it. I didn't know it existed, so I started scraping it myself, but that's better. It also includes Milan, so it's completely pointless to scrape BikeMI. Then you have open data from the public administration. Milan has one. Every big city has it. You also have it from Lombardy or from Italy or the European Union, pretty much everything. This is a cool example I found on the Milan open data website. They give you a big JSON with all the trees that exist in Milan. So you have 250,000 trees, not the ones in the parks. And for each one, they tell you the species, the coordinates, of course, the size, the year, actually also the date when it was planted. I don't know if it's accurate. I didn't do anything yet, but it's quite an interesting source of data. And then we have the big source, OpenStreetMap. Just by raising your hands, how many of you have never heard of OpenStreetMap? Okay, we have 3-4 people, that's already good. Otherwise, you would be bored. Also, maybe even if you used it, even if you know about it, you don't know it well. OpenStreetMap is essentially for maps what Wikipedia is for encyclopedias. So it's a huge map of the world where people contribute, and most importantly, the data is freely available to download. So you can download it, and you have map data for pretty much all the world. It's also used by everyone. Strava, Komoot, Apple Maps, and many others use internally this data. So you actually are using the same data. It was started in 2004 in the UK, but now covers everything. And one thing that you maybe not get when you see the map, here it just looks like Google Maps, so just a map, is how detailed this is. So for example, this is the result of an application called AutoFocus, which shows you the tags on the phone. And this is the area where we are. You can see that for the M2 lines, we can see the voltage of the tension of the cables, the gauge, the scartamento, so how the distance between the rails, the name in different languages. You can see the type of pavimentation on the Corso Como, it's set. You can see the times of the shops, pretty much everything. A lot of stuff that is very hard to explain, but they have it. This is, of course, if somebody took the time to insert it, meaning that in Milan it's quite good. If you go in rural areas, it's less good. But there is a lot of stuff that you can actually use in here. And just be aware that if you want, you can contribute to OpenStreetMap. For example, with an app like Street Complete, you can easily, without knowledge of how database look like, they show sort of quests, so quick questions, and you can easily expand the map, especially if you are outside a big city. I don't want to go too much in detail about how OpenStreetMap represents the data. Just be aware it has nodes, which are latitude and longitude, so points in space, which are aggregated into ways. So basically, a set of nodes that can make, for example, a street or a building. So 4 points that define the perimeter of the building. And then relations, which are an aggregation of ways and points to define stuff that is much more complicated. For example, the whole rail network, so something that is quite complex. And all of these nodes, ways, and relations has a set of keys and values, so tags. Everything is defined like that. So for everything that you want to describe, the opening hours, the surface of a walkway, whatever, there is a tag and a key and value that describe it. This is an example. This is the U6 in Bicocca. This is quite a complex shape, so it has holes, which is a pain to handle if you do it manually, like I did in the past. This is a relation, and you can see here there are 5 ways, so the 4 holes plus the external perimeter, and it has a few tags. So the tag building is set to university, tag building color is set to the color of that building. It has 4 levels, 4 floors. You can see the website of the university and stuff like that. Okay, and for everything there is an ID, and you can visit the link. So if you click here, you see this page. So for everything, you can see how the data is represented. Okay, that's cool, but how do we put this into Python? So for small things, they offer an an API called Overpass. Overpass, it's very simple to use. You just have a package, you send a query, and you get results. This is, for example, a query to get the boundaries, the perimeter of Saxony. You can do also more complicated things. For example, if you want to do a bank robbery, you can easily find banks that are at least 3,000 meters far away from a police station. So you can just send this query to a service, you get a result, and then you process it in Python. I find this is the ugliest query language of all time, because this is how you assign a variable. So the variable is on the right, and it's not very readable. The errors are not readable, but it exists. And for small things, you can find examples around, and also ChatGPT get it right. So you can, for small things, it's fine. An alternative is QLever. QLever is sort of ontology, it's a graph database that can query also this kind of data. So it can actually merge different types of data. It's quite powerful. It's also very verbose. So this huge query, the first part is just a boilerplate. The rest is saying, okay, we have an element, which is like the x in an equation. So it's something that you want to find. We said this element is contained in this thing, which is the Philippines. This is the ID of the Philippine relation in OpenStreetMap. Then it says that that element is a newspaper office. And then we say we want the geometry. So basically, this query is asking it to find all the buildings that are newspaper offices in the Philippines. The cool thing of Clever, if you can manage to use it, is that you can integrate data from different sources. For example, you can say, give me all the streets that are named after people who were born in the Middle Ages, something like that. You can do it if you figure out how to write the query, because it can join with Wikidata. You can also process this data with GeoPandas, which, as you can guess from the name, is just pandas plus some geographical capabilities. It can store geographical data, geometries, in addition to the usual data you can process. The nice thing is that, like pandas, it works with Jupyter, so you can have something interactive. I don't really like pandas, so I also don't like GeoPandas, but it works, and it has the same advantages. Of course, it works as long as the data fits the memory of the computer, but that's often the case. In case you're wondering, there's also GeoPolars, which is polars plus some geographical stuff. Okay, all of this works if you have not a lot of data. In reality, now you can process easily a whole city like this. You can use GeoPandas and it's fine. So in the past, it was more a problem, but now every computer can easily do it for a big data set. But if you want more data, or if you want, you cannot accept the latency of Overpass, which can take a few seconds to reply, if it replies. You can actually download the data on your computer and process it locally. And all the data in OpenStreetMap is available as a big file, which is the latest the planet latest os.pdf. This is 90 gigabyte, so you can download it, but it's not easy. There is a website, there are many, but there is one most famous, which is GeoFabric. They allow you to download extracts. So you can get the file only for Italy, only for France, sometimes even smaller areas inside the country. And that's where pretty much everyone gets the data. The format is protobuf, it's based on protobuf, so it's very, very efficient in representing data. And to handle it, you can use the osmium command line tool. So with osmium, you can say, okay, I want, for example, in this case, to take the France file, which is probably large, still probably 2-3 gigabytes, and extract only an area with the coordinates defined there, which would be parts. So you can just handle this file, do some statistics, slice it. And if you want to process in Python, there is a wrapper called PyOsmium, which is actually quite easy to use, even if it's a very low-level tool. This is an example that prints all the amenities, so shops, schools, hospitals, everything that is of public interest. And for each one, it provides the coordinates and the name, if it's possible, and the type of amenity it is. All it does is it needs to read a PDF file and just process it. And this scales very well on large files, so you can process the whole planet, because this is, if you recognize a pattern, similar to a SAX parser. So it just goes to the list and iterates over it, so you don't need to load everything in memory. So it works well with a lot of data. Another thing you can notice is that all this magic code loads a WKB, which is a well-known binary. So it's the way many tools like this give you the representation of the geography. So they give you just this string. But we don't need to handle this WKB ourselves, because there is a library called Shapely that can read it and give you some object that represents the geographical data. So in this case, it's the polygon. And when you have it, you have a lot of methods like representative point that gives you the center. You can generate an SVG with the print of the image. You can generate a GeoJSON. So Shapely is basically the library in Python to do geometry manipulation. It can do everything you can imagine for geometries. So it can tell you areas, perimeters, can tell you if a point is in a shape or not, can tell you the intersection between two things, if it exists, everything. Internally, it uses the Geos library, which is the same used by PostGIS, which you're going to see. So it's a very, basically the thing you use to process this data in Python. And then we have, of course, PostGIS. PostGIS is a Postgres extension, so it's a way to extend a Postgres database. The nice thing is that it doesn't change the way the database works. It just adds stuff on top of it. It gives you two data types. Geometry, which is just a new type that represents geographical data. So it's you can have points, polygons, multi-polygons, which is polygons with sparse parts, and pretty much everything you may have in these data sets. Geography is just geometry plus some metadata, which would be a talk by itself, but basically geography just tells PostGIS how to handle the fact that the earth is not flat, to calculate distances more accurately on big areas. Special indexes, which are necessary, because if you have geographical data and you want to query it, so you want to find what is at some point, what is the area, and you have a lot of elements, you can have millions of elements in a country, indexes, you cannot just do a where and do search dumbly with coordinates, so you have to use a special index, and that's provided by it. And then you have a lot of functions that handle this data. For example, all these functions that starts with st underscore are provided by PostGIS. Still, behind it, there is Postgres, so you can have all the features of Postgres, transactionality, async transactions, everything is just provided. And this is an extension that is by default installed, available in AWS or Scalewell, so you can just have it everywhere. And there is a Docker image for PostGIS, so it's very easy to use. In the end, it's just Postgres plus some stuff. And there is a tool called OSM2PGSQL, which can take a PDF file and load it into Postgres with its own table. It works directly, but if you want to do something more sophisticated, I can suggest pgonflex, which extends it with some Lua script and gives you a nicer database layout. This is an example of how a real PostGIS query looks like. I don't know how readable it is. Maybe is it better? So this is in the end just SQL. So it's nothing special except this st underscore stuff. It takes this big planetons polygon table, which contains all the polygons that it found in the dump, and joins it with itself. The first time it takes it is to take the buildings. So it checks that something is a building, it's not a river or something like that. And the second time it takes it is to find Italy as a shape. So basically, it's first trying to find the polygon that wraps Italy. It's not necessarily a polygon, it actually can be complicated. For example, Italy has holes because there is San Marino and Vatican City, so it considers that. And then joins them with this condition, st underscore intersects. So it checks that two shapes touch each other. And if that's the case, it means that the building is in Italy, or touches Italy, actually, could be on the border. And this then sorts everything by area. So it gives you only one element, which is the biggest building in Italy. Do you know the answer? What is the biggest building in Italy? I had no idea. I searched it. Is Lingotto. It's a building in Turin called Corpo Uno. And this query takes like 500 milliseconds. It's super quick because it uses spatial indexes. In Python, you can just use PsychoPG3. It has an adapter So basically, whenever it finds a column that is geometry, it gives you a shapely object. I made a pull request to do it. So it's very easy to do. Also, you can use a syncpg, anything else. They just work. They give you the WKB and shapely as a method to convert it to a shapely object, and then you can do whatever you want with it. Alternatively, you can use DuckDB, which is my favorite. In fact, that's what I use for the example of the travel assessment. DuckDB pretty much has the same stuff as PostGIS, but much less sophisticated. So it has the geometry data type and implements st underscore stuff, pretty much with the same syntax. So the queries work more or less the same. It just lacks some functionality. For example, for my traveling problem, I needed st underscore segmentize, which is a function that takes all the long segments and split them into smaller segments, because that's necessary to do routing, because you need to find a starting point, and if a road is 1 kilometer and you're in the middle, it doesn't know that you can go actually in the road, and that is not present. So I had to take the objects, put them in shapely, apply segmentize there, and put them back. No, just 2 minutes. To ingest into DuckDB, you can use 2 different tools. DuckDB Osmium just reads PBF as if it was a Parquet file, so you just read it and you see everything in there. QuackOsm is quite a powerful tool that can directly take a PBF file and generate the DuckDB database without any extra step. You just go from one to the other and then you use it. You can also convert to other formats. This is an example. I think we're already on the edge, so I'm actually not doing it. But you can just download Italy, which is just a single file, convert it with a DuckDB database, which takes a few minutes, but then it generates this database file with a table, and then you can query it. In this case, the question is how many cities in Italy have a street called Via Roma. Via Roma is the most common name for a street in Italy. This is the query. So first I get all the comuni, which means I find all the elements that have the tag called admin level equal to 8. Admin level is how OpenStreetMap calls basically hierarchical administration boundaries. 8 is comuni. Other numbers indicate regions, provinces, stuff like that. So I say, okay, find me all the comuni, so all the level 8. And then I find all the geometries that have a name which is I like, so insensitive matching with Via Roma. And then I output the result as well, actually not outputting it, I just showing the names of the comuni, so not showing the shape. For the other case, I did produce the GeoJSON. So this function gives you the JSON that you can then easily look at. One thing that is a bit obscure is this 4326. Why is there? Because by default, when you import data into PostGIS using this thing, OSM to BGSQL, it uses a projection, so a way to represent data, which is called Web Mercator and used by most tools. But GeoJSON wants another projection, so you need this trick only once. Otherwise, you get coordinates that are not the usual angle coordinates, like 43 degrees north, 9 degrees east, but coordinates in meters, so I need to do this conversion. Okay, once you do processing, whatever tool you like, you need to display the data. So you need to actually show it to the user. And this data is quite annoying to display, quite annoying to read. So you can read a GeoJSON, but it's really a list of numbers, so it's not really usable. The easiest way, the first thing to do, especially if you do troubleshooting, is to use GeoJSON. Every tool, Shapely, PostGIS, DuckDB, can export data as a GeoJSON, which is just a JSON. The browser can understand it. Pretty much every tool can understand it. And then you can just go to geojson.io or one of the 20 websites that do the same, and you load the data and you see it. In fact, the screenshot that you saw before with the path in Milan was made with geojson.io. Just load and see the data. Also, if you need something more complicated, you will need a base map. So you need a map, and the data is shown on top of it. This is what you do, for example, for a heat map. or a choropleth, which shows basically stuff like population density, or the heat map we saw before. If you use GeoPandas, they just use some anonymous map service, so they can load data without an account, stuff like that. But this works only for small use cases. So if it's on your computer, that's fine. But if you, like me, want to show it on a website, you may have multiple users, so you cannot just rely on some mysterious anonymous service. You need either to self-host or to have an account on some provider for maps. A map that can be zoomed and moved around is called Snappy Map, and that's basically what you need. One way to do it is to use raster tiles. So essentially, you have a single big PNG image that represents the world, so just a map. And then you say, okay, this is zoom level 0. Zoom level 1 means that we split into 4. So we have 4 tiles, 4 images that represent the world. And we call them 0, 1, 1, 0, 0, 0, 1, 1. Then we increase the zoom level. And every time we have a new set of images, always more and more, because we are zooming. And we store them into basically a set of folders. In reality, you can have some database behind it, but it doesn't matter. You will have, in the end, some address like this. So for every zoom level, you have an X and Y. And that's how initially most services did work. So when you move around, the browser just knows where you are. When you use the mouse, the browser just loads new tiles, meaning that the browser has to do nothing. It's just dumb, just loads the images and shows them. This works. The problem is that it's extremely inefficient. So over time, people switch to another approach, which is vector tiles. The idea is still the same. So you have a set of folders with all the world represented into small files for different levels of zoom. But this time, you don't have images, because if you think about it, 70% of the surface of the world is water, meaning that you have millions of images that are just blue because they all fall in the sea. Vector tiles are much smarter. They represent data in protobuf, so it's actually telling the browser what is there. So saying, okay, at these coordinates, there is a point, a polygon, and this polygon is representing a river or a street with its name. And then the browser has to render it on the fly, which means that the browser has to do a lot of work, but the file is much smaller. And the cool thing for us is that you can customize how data is displayed without recreating them. So if you decide that the sea has to be displayed in gray instead of blue, you don't have to recreate all the tiles. You have only to tell the browser, look, when you see that something is sea, it's now gray instead of blue. And you can also have stuff like 3D buildings, colors. You can change the language on the fly, all without changing the tiles again. You just change how the browser loads them. They're standardized. There is a format called MVT, and many providers offer it. So if you use Mapbox or Tyler, which are 2 big providers for this data, you can switch from one to the other, so we don't have vendor lock-in, just use any library. What I suggest is use MapLibre, which is probably the most sophisticated front-end library to deal with stuff. Then there is Protomaps, which is, it doesn't change it just extends. Is a way to store the whole world into a file, which is then served from S3. So you just put all the tiles together in a big file, and it uses some black magic to basically represent every tile at a specific point in the file. And then HTTP supports range request, so the browser can point to a specific point in a file, and this makes the whole thing a lot easier to handle. This is what Flixbus uses. So we use vector tiles with Protomaps, and basically you download a file and you have a map of the world that you can host on your computer. Then if you want to experiment, MapLibre also started a new format. They started just this year, so it's very new. In theory, improves the quality and the compression, it adds GPU decoding. In reality, it's still very hard to work with, so you may want to have a look at it, but it's not yet there, in my opinion. If you use MapLibre, which is what I recommend, it's extremely easy to add a heat map. You just need to provide the base map, the data as a JSON, and then parameters like the scale, so how dense or not make it, and it works out of the box, so it's super easy to do. And it's completely customizable. You can see in this case that they they don't have any, they have this sort of pass the core map, that's doable. Same with choropleth, which is this kind of representation where you have polygons with different colors and you just overlay on a map. That's very easy to do in MapLibre or similar tools. And you just need to provide a GeoJSON. So you just provide this JSON with the data and it appears on top of the map. Then, just to mention it, actually, we're not going to see anything like this because this is a huge new world. There are services that provide you images of what is around. One of them is Mapillary. Mapillary is operated by Meta, but they have an API which is open and the license is permissive, so you can actually use it. It provides pictures of pretty much every street taken by people who uploaded it. If I uploaded this picture, it's close to my home. They have an API, so you can easily do image processing. For example, here I put the link to a presentation done by somebody I know, in which they used Mapillary data to analyze through Python and some machine learning, computer vision, the quality of bike paths in a city. So they already do it, and a lot of this data is already provided by Mapillary itself. So you can easily ask the APIs where they did detect something like a camera, a street sign, a manhole, a pole, something like that. Okay, so this was just an overview. I hope it's a bit interesting, and I didn't go either too in detail or too quick, but that's what we can do in the time. So this is the link to the presentation if you want to see the link, so you see it for yourself. And if there are questions, you can ask. Okay.
During the presentation, you mentioned that it used to be really. Oh, sorry. So during the presentation, you mentioned that it used to be hard to calculate large data sets on large data sets because computers were not as powerful. So with the LLMs and all the technological progress nowadays, how do you think, what would you think could be possible? How do you see the field evolving and such?
So I'm seeing that more than LLMs with stuff like Parquet or DuckDB that really optimize how data is represented. You can probably do everything with a city or province, never storing it on a disk. Just give everything RAM, that's okay. I would use still a database like PostGIS if I wanted to integrate with other data. So if you want to make an app that actually offers something to the user, so in the case you need to do joins, transaction, all the stuff, and then you still need a database. But for the size of the data, a city or even a region with a normal computer is completely fine, usually, yes. The word, 80 gigabytes is still a lot, but yeah, once you filter for it to care about, it's very small. I think there is a link somewhere with the example of Milan, and that's 80 megabytes of map. So it's very small. And that's the tiles, so it's already rendered.
Oh, hi, thank you. So going back to the isochrone Voronoi with the metro stations, just out of curiosity, were there something like enclaves or holes?
Yes, that's a good question.
I was just curious about that.
Yes, totally. And in fact, we can even see it live. So the question, just to clarify, I think, is if there are areas that are contained in other areas, so if they're not contiguous, yes. You can already see from the image, but we can even use the interpreter if it works. Yeah. Okay. Okay. So. So yes, there are enclaves. For example, here. This one, I have no idea why, but many others. I don't remember where they are. So here you see the shape is quite a mess. If I move around, I see this as a very distorted border. And this is normal because if you use, for example, tram to move from here to here, then maybe it's easier from here to reach this area, but from here it's already not convenient because the stops are not linear. In general, if you consider public transport, everything becomes a mess because you have schedules, you have no linearities essentially, so the shapes can be very weird. But that's completely normal. Yeah, here there is an article that I wrote about this because it's quite complicated. But basically, I create a grid and calculate the positions from every center of the grid. So that's why it has this very strict shape. But yeah, that's pretty much how it works. And this is calculated assuming you start at 3 p.m. on a Tuesday, because of course the schedules can change. Okay. Any questions? Okay, I think we have the other speaker, I hope. Thank you.